Hello everyone, the stream is live. Hello everyone, if you are watching, please come and say hi. Hello. Hello, hi. Hi everyone. Yeah, we have some music already playing. Yeah, so for those who are already here, this is what I plan to do for today's stream. So basically, this is a new series that I'm experimenting on how AI works. It's gonna be more on explanation and educational content on AI and large language models, on how they work, and hopefully it will be very helpful for people, because I realize a lot of people don't actually understand how they work, and if they don't understand how they work, they can't use them very effectively. Yeah, so that's the rationale behind having this stream, is to teach people how these things work. And now, what other better topic to start than LLMs themselves? So today I'll be covering how can you train your own LLM, right? So this is gonna be done through training our own GPT-2 model, sort of, with a project called nanoGPT. So let me go through this introduction on what is GPT-2 and what is nanoGPT. So for those of you who don't know, OpenAI is actually a very old company. They have been around since 2011 or I think 2015 or somewhere around that. And they have open sourced a model called GPT-2 in 2019. As you can see, this was the precursor or predecessor for what has become GPT-4 and GPT-5. GPT-2 was actually released 6 years ago. So this GPT-2 model, believe it or not, is open source, and it was the latest open source model until they released GPT OSS 120B, which is a few days ago. So this was arguably what started it all. This particular repo is quite hard to understand. I think it's very optimized for running and not useful. I mean, you can run it, but there's a lot of problems because it's 6 years old. So instead of taking a look at this particular repo, we will just be taking a look at this particular repo, which is done by Kaparthi, who used to work for OpenAI, and this is a very popular reproduction of GPT-2 with a much simpler implementation and easier to understand, right? So we'll be taking a look at this repo to train our own model. One interesting thing is it appears that Kaparthi is experimenting with Devin. That's interesting. So you can see some commits made by Devin. We'll definitely be checking that out later, I guess. So in order to fully reproduce GPT-2, you need some GPUs, right? Because even though it's 6 years old, it's still quite a large model, and you need some GPUs to run the full GPT-2 reproduction. For me, actually, I have already done that before. So this is a training I did, I think, a few years ago. This was done actually 1 year ago, last year, to reproduce the GPT-2 results. So as you can see, it does work. So this project does allow you to train a model that is very similar to GPT-2 performance. and I did have experience running this repo and getting it to work. So it's a very good starting point for people who are trying to learn how these things work, right? So that's the introduction. So I already cloned the repo into my local, and we can take a look at the README to understand how we run it. I think it will be quite short because I will be walking through this anyway. So basically you need to install some Python libraries, and then there's two ways to run it. The first way is if you have a GPU, you can actually reproduce the GPT-2 result by training it on a open web something. Open web text. Yeah, so you can train it on open web text, which is about 8 million documents inside. So this is the proper way to reproduce GPT-2. However, if you only have say a CPU like me, you only have a MacBook, you can also run this by training on a Shakespeare selection of work. So this one is much smaller, Shakespeare. I think it's like somewhere along the line of 1 megabyte of text consisting of Shakespeare's work. So this is a much smaller training data. So it just have Shakespeare's writings, and then you can train a model on it, which is very fast. So that's if you don't have a GPU, you can try to run this and it will work. So in fact, why don't we just run it right now? So let me just show you how easy it is to train a model. So the first step would be to download the Shakespeare's writing, right? So I've already done this before, but let me just run this. You can see you'll basically download the Shakespeare's work and then run a tokenizer. So it will run a sorry, this is not the tokenizer part. I think this is the oh yeah, it is the tokenizer part. It will tokenize it into GPT-2 encoding and then give you the training data. So, and then with this training data already, you can actually train it. So I have a MacBook, so the recommended way is to use MPS, which is specific to MacBook. And if you don't have a MacBook, you're running Intel, you can run with CPU. So I'm just gonna run this, and then you can see it's actually training. And then if you're familiar with machine learning, you can see the loss is actually going down from 2.2 to 2.1, and then it's becoming 1 point something. So the loss going down means that the model is getting better. After I think a while, it will just hit the end. I think 2000 iterations, and we got a loss of 1.69. Yeah, so that's how we basically train on Shakespeare's work, and then we can verify that we have already trained this by running Inference, right? So this is similar to how you run ChatGPT. So you give it a prompt. So this is actually a little bit different from ChatGPT because this is a base model that is not instruction tuned. So it basically auto completes your sentence, right? So for example, if I give it a prompt or starting the sentence with king, then it's gonna try to complete the sentence after this king and then continue writing there, right? So show you an example of how it works. So I start with king, and this is a base model. It's gonna try to predict what comes next, right? So it will actually say something like king of death, blah blah blah. So this is pretty gibberish because we just train on Shakespeare's work. Anyone want to try some other starting words? because it's trained on Shakespeare's work, so it have to be something that is, I guess, classical, then it will work. So maybe we try to start with something interesting, maybe a second. So if I start with second, you can see that the model will start the sentence with second and try to complete what comes afterwards, right? So it will just be a second and a period, and then something else. So it's not very intelligent, but it is how these LLMs work. So that's a very basic sample run of how you can train a large language model. I mean, it's pretty small in our case, but the concept is the same, right? So basically you train a language model that can autocomplete. And then after you, this is the first step actually, which is called pre-training. And then after you have done pre-training, you get a base model, which is like a checkpoint file here. And then you do a post-training, like supervised fine-tuning, instruction tuning, to make it like a chatbot. So then you get ChatGPT, right? So this is the step one of two-step process on how to train LLM. But that's not the purpose of this live stream. Otherwise, it will be too short. So we have run the code and make sure that it is actually working. So let's see how it actually works, right? So this is the more technical side of things. So let's take a look at, let me see my notes. Okay. So the first thing to look at is the tokenizer, right? Tokenizer is actually a very important part of LLMs. So you can see here, the tokenizer is prepared with the training data, right? So in this case, our training data is Shakespeare's data set, and then we tokenize it with the GPT-2 tokenizer. So this tick token is actually from OpenAI that helps you to encode the text into tokens, right? So what are tokens? So I have this example website. So basically, you have some words. In order for the model to understand it, you have to tokenize it into tokens. So you can see these colored blocks are the tokens that correspond to the characters or words. And then these are the actual token IDs, right? So it will just tokenize all the words into token IDs. For example, many will be tokenized into 12488, and then this space words will be tokenized to 6291, right? So on and so forth. So here we are doing the same. We're trying to tokenize the training data. So we have a training data and a validation data. The training data is the 90%, and validation is the last 90%, the last 10%, right? So we can actually print this. So let's try to print this. Okay, so we're just gonna print the tokens and then see what they look like, right? So let me try to find the prepare statement. Okay, sorry, this isn't, I modified the wrong file. It is the correct file. Oh, okay, it's running the other one. Oh, this is the simpler training. Yeah, sorry, I mistook. So this is actually the simpler training that doesn't involve the. It looks like it doesn't involve the tick tokenizer. It's just training. It's just giving it a numeric value. Yeah, so actually for this Shakespeare one, right, we're not using the tick token. We're just encoding it with some numeric value, because the vocabulary size is only 65. these are all the unique letters. So basically all the letters and all the special characters, and then we're just encoding it to like numbers lower than 65. So because of it has 65 unique characters, we assign one number to each character, and then we get a encoding of just 0 to 65, right? So that's the simplified version if you train on Shakespeare's set. But if you train on the open web text, then it would actually use the OpenAI's tokenizer to tokenize the text. So basically what you get out of these IDs is just this series of numbers, right? And then you store them using Pico, which is a serialization library from Python. So I think if you are used to machine learning work, you will know this kind of thing. So you're just dumping the binary data. So that's the tokenizer, which is to prepare the data. And then second part, I think we also need to cover a bit of PyTorch. So if you have never done a machine learning training, this is some prerequisite to understand before we can go into the GPT model. So let's take a look at the GPT model itself. So this is a GPT model, and then we have a few classes, right? We have a few classes, layer norm, causal self-attention, MLP, block, and the GPT model itself. So the GPT model itself is a module, which is a neural network module, and then all this block, MLP, causal self-attention are also an module. So an module is a module inside PyTorch. So we need to take a look at this module to understand how the training works. So if we click onto module, we can see this is a base class for all neural network modules. So if you have trained a neural network before, this is quite easy to understand. But if you haven't, I'll just give you a brief overview of the important methods. There are a lot of methods here, but essentially the one that is very important is the call method. The call method is called when you run this model, right? So when you run this model on an input, it will give you an output, which is like how you run the inference. So if you take a look at the GPT model we have here, here. This is the training code, and if we found the important stuff, which is here, right? So basically you're trying to train a model to kind of make it become better. You have to give an input and the expected result, right? So this is how you train a typical supervised learning model. So you give X and Y. So this X and Y will help you train the model become better. So this is your training data, and then this is I think what you expect the model to output, and then by computing the difference between the training data and the expected output, you can kind of make the model get better. Or I think I might have used some wrong terms, but I guess you get the idea here. So if we go back to this call method, we can see what it's actually doing. So it's just calling the call implementation, which after a bunch of things, you can see that it's actually calling a forward call, right? So if we look at what forward call is doing, it's actually just calling the forward, function. So that's where you can connect how it calls the function and then go to the forward. So okay. So now we go back to the GPT model. We can see that it has a forward function, right? So this is where the most important thing happens. So the forward is gonna take an input and produce an output. So similar to how you write a normal function. So this is how you run inference, right? So basically when you run ChatGPT, what happens is your prompt will be somewhere here, and then the forward will give you back some probabilities that maps to certain outcome, and then you get back your ChatGPT response. So basically what I'm trying to say is this forward method is how you run a model, and how it gets called is feedback, basically calling the model itself here. So that's basically how it runs. Yeah, and then there's also a backward, which is very important. So if we look at the model here, we have a let me see. Oh, sorry, the backward is not here. I think it's somewhere else. I think, oh, sorry, the backward is handled by outside already. So I guess the important thing for model is just the forward call, and other things are kind of less important. And then for the GPT model itself, we have the forward call, but we also have other things like block MLP, auto self-attention, and layer norm. So what do this do? Basically, you can see here, when you initialize a GPT, there's a self transformer. So this is a kind of internal state of the model. Where you initialize a bunch of embeddings, and H is actually the, I think, layers. I guess you can call them layers. So we have the vocabulary embedding, block embedding, dropout. These are, I won't go into details, but you can see here, a transformer is composed of these embeddings and a list of layers of blocks, right? And a layer norm. Can you tell me what you are doing? I'm trying to walk through the code base of a nanoGPT to explain how to train a language model. Yeah, so basically you can see a GPT class contains this block module, right? Because the H is just a list of block. And then what is a block? So block is the one layer norm, one attention, and one layer norm, and MLP, right? So it composed of layer norm, attention, MLP. And then the forward, which is how you run it, is basically itself plus the attention, plus attention of layer norm, and then after you do this, and then you again plus MLP of the layer norm. So what this actually translate to is actually if you go back to the transformer architecture, you can see it's basically doing this, right? So you have this your input, and then you add layer norm, and then for the next layer you add at the layer norm and keep doing this until n times. So it's basically doing that for each block, right? And then within each block, you have the attention layer, which maps to this part of the GPT model. So this is the architecture for the multi-head attention, and then it will map to this causal self-attention layer. So I won't go into the mathematics, but basically the important thing is, again, inside the forward loop, you have batch size, sequence length, embedding dimensionality, and then you're basically doing a bunch of matrix transformation and matrix multiplication, which all this is just basically mapping to the math here. So this is basically implementing this matrix multiplication. Yeah, so I guess it's time to talk a little bit of this attention mechanism. So I won't go into the math of the attention mechanism because it's gonna be very hard to explain without some prerequisites. But there are some online explanation that I found which can be helpful in understanding how this works, right, intuitively. So basically, this is a somewhat good explanation of attention mechanism I found. So basically, it's trying to solve help model understand the context. So yeah, thank you very much. It's very complicated, but I'm trying to make it understandable for normal engineers or technical people. So there are two examples here. So one is the bank of a river and money in the bank. So these two words are both have bank, right? But they are clearly have different meanings. So by computing and attention, basically when the model reads the word bank, it considers other words in the sentence, right? So for example, we have money in the bank, and then we add attention, and then the model is gonna understand, oh, this bank means the bank that has money, right? So this is basically how the attention mechanism works. Hello, Jun. Yeah. So this is a very intuitive understanding of how attention works without going to much mathematics. I think I have another explanation of attention. So let me see this one. Oh yeah, so basically before we even talk about attention, we need to talk about the positional encoding first. So basically the positional encoding is happened here, right? So we have the block size. I think this is the positional encoding, and then you pass it to the self-attention, and then this one gets the positional encoding, and then does a bunch of matrix multiplication. Let me find it. Okay, here it is. So when we have a query key and value, so the query, and then we multiply them, we will get a dot product of query and key, right? So what are these queries? The queries are the vector representing a specific word, and then the key is, I think, vector in attention corresponding to each word or token in the input sequence. I don't really understand this, to be very honest, but I think we don't really need to understand this to understand on high level how it works. So basically, if we multiply these two together, we get a score of how relevant each word is to the other, right? So we multiply this, and then for the word how, it's relevant to R, right? And for the word R, is relevant to how and U, and for the word U, is relevant to R and less relevant to how. So basically, by doing a matrix multiplication, we get a bunch of attention scores to know which words are more important than other words. Yeah, so yeah, maybe I'll do another more technical dive on how exactly the query key and value works. I think this is a good enough intuitive explanation. Let me see, I have another explanation here that is possibly more interesting to look at. I think, let me see if, yeah, so the query is asking for information, and the key represents content, and the value is delivering content, right? So these are the three components. From a mathematical perspective, let's see if we can find a good explanation of what they are. Yeah, sorry, it's a lot of content. This is just the embeddings, which we already covered. I find a good explanation on the query key and value. Yeah, sorry, I don't think I can find a good explanation on how you get from the embeddings into a query key and value. But yeah, so for that part, I guess you have to read more on yourself. So I will be moving on to the model itself. Let's see. So after we get all this, after we done all this matrix multiplication, we get layer norm and MLP, right? So after we get all the attention and understand their positional importance, we just pass it into MLP. MLP is much easier to understand. It's basically like a simple neural network. You have some linear layers, and regularizer is DLL here, and then the forward is just doing a bunch of computation. So you do a linear layer, and then you do this GLU, and then you do another linear layer, and then there's a dropout. I think the dropout should be 0 in this case. Yeah, so basically a block has a MLP, and then inside the MLP it's just a very simple neural network. The magic actually happens in the self-attention layer. So basically, if we go back to this diagram here, so this is the linear layer, that is the last step, which maps to here. Yeah. And then we can talk about the GPT model itself. Let me see. Is there anything else inside the GPT model that we need to talk about? Okay, so basically, we can look at some of these configs to understand what they do. The block size is actually the context length, right? So a block is like how much you can fit into the model. So 1024 means you can fit 1024 tokens into the model, and then if the sentence is longer than 1024, then the earlier tokens are lost. So this is basically the context window that we know. I think the current models will be like 64K, 200K, 1 million, those. But for this case, we only have 1024, right? So it only knows the last 1024 tokens. And the vocabulary size is basically how many tokens you have in your training data set. I think these are the two important understandings. If you want to understand how the model works. And then let's take a look at how you can actually train them. Okay, before we look at the training code, we can take a look at the inference code, right? So assuming we already have the model, how do we run the model so that we can get some text as output? So I believe that's kind of related to the forward, which is how we get the model to run itself. And then there's also a generate method, which is more for generating a sequence, right? So basically, you can see here for each token, how do we generate the text? Basically, if you use ChatGPT, you know it generates like token by token. So how do we get these tokens? Let's see. So the important thing is to run a self on this. So if you remember from earlier, when you run a self, it basically runs a forward pass. Forward pass is defined here. So when you run a forward pass, you get back some logits. Logits are basically probabilities of tokens. So you get a probability of tokens, which one is more likely to happen. These are all probabilities. And then once you get the logits, and then let's see what actually happens here, right? So this is where the temperature comes in, right? Yeah, so you scale by the temperature. I guess the higher temperature means it's more likely to pick any logits, and the lower temperature means it's more likely to pick the top logits. So basically that's an intuitive understanding. I don't really understand the exact operation here, but that should be what it's doing. So you can see here the temperature is applied in the last step, right? Almost at the last step. So this is where the top K comes in. So if you play with models, you know models have top K. Basically, it's just trying to pick the top K responses and discarding the rest, right? Let's actually try to understand what temperature. If temperature is 1, that means division doesn't really do anything. But if the temperature is low, then the logits will all be very low, right? I guess. Yeah. Maybe let's ask cursor what this, right? What does this line do? I think maybe cursor will give a good explanation. Let's try a non-thinking model. Okay, so this is the batch size, and then this is the last one, and then all vocabulary dimensions. Last tokens logits. Okay. Divide by temperature makes the distribution more peaked, more deterministic. If it's higher than 1, more flatter. Let me see if I can understand this. So this is the last logit. the last token, right? And then you divide by temperature. And then this is still a list of probabilities. And if the temperature is very low, let's say 0.001, that means the probabilities are going to be much higher, right? So I guess it means that if the probability is already very high, then it's gonna get even higher. I think so, right? So let me see if I can put this into perspective. For example, the probability is 0.2 and 0.1 and 0.001. After you divide by 0.1, and then this will become 2, right? So this is 2, and this becomes 1, this becomes 0.001. It doesn't change the Does it change the distribution? I don't think so, right? So I must be missing something. Distribution more uniform, leading to more random or creative output. How does a division help? Okay, I guess we can just try it out, right? I mean, we have the code, we can try it out. So we can just print the logics here, and then we can print the logic afterwards to take a look at what's actually happening. Let's see. Okay, so we have some logics here. Let's make it more explicit, right? It's in, and then have the logics out. Okay, and then I guess we can do the pretty print tensor. Okay, never mind. I forgot how to pretty print them. So let's take a look at the actual logics. So for example, here we have all these logics. Okay. Oh, I think we also need to print the temperature. Let's print the temperature. Can see how does the temperature affect this. So the temperature is 0.8, and then this is basically divide by 0.8, right? So if we divide this by 0.8, we get 6.66. So this is correct. So how does divide by 8 modify the distribution though? It's quite puzzling to me. Like, maybe my math is not good. How does division by a constant affect the distribution? Let's ask Cloud to understand the math here. Oh, because we have softmax. Ah, okay. I see. We have softmax after this step. Oh, okay. Now I understand. So after this division, we get. So for example, if the temperature is low, you get larger differences, right? So basically, if you look at this example, so the difference before this is 0.1, and then afterwards is 1, right? And because of the softmax, softmax is just a function, right? Activation function. Because of the softmax function, it actually maps the output to be more different if the difference is larger, right? The absolute difference is larger, I think. Yeah. So yeah, this is a good example, right? If we have 2, 4, 1, and then at the lower temperature we get this kind of output, and then after we apply the softmax, basically the probability looks like this, right? The final probability where everything must add up to 1, I think. Sorry, not everything add up to 1, but everything is below 1 will become like this, and then the center one is more likely to become selected. And then if we have a temperature that is very large, like 2, right? And then, you know, all these 3 are like, I mean, the center one is less likely to be selected compared to before, right? So before it has a 97% chance to be selected, but if you have a temperature of 2, it only has a 46% chance to be selected. And then the other options are more likely to be selected. Yeah, so that basically explains why if you have a higher temperature in your model, the output is more creative and random, right? Compared to have a lower temperature. So yeah, I'm very glad that we tried to explain this, because this is actually very useful for application, right? If you understand how the temperature works. So it's basically a division of temperature of the raw logits. The raw logits are not bounded to 0 to 1, right? I think they can be some other values. And after the softmax, the distribution indeed becomes different. Okay, that's pretty cool. So we have the logits, and then after we get the top k logits, we apply the softmax, and then we sample from the distribution. So these are all like standard machine learning stuff. There's multinomial sampling, and then basically we return the index of the token, right? Which is like a number. If you still remember what tokens are, so it basically returns like a value here that will map back to some letters. Okay, so that's basically how you run the inference, which is the easy part. That's the inference part, and then we come to the training part, which is how you train a model, right? So this one is gonna be much more complicated. Again, this is the model file. We have to look at the actual training file. So all those previous steps are just preparation for the last step, how we can train the model, right? But actually, if you understand how the model works, then the training becomes much easier to explain. So these are DD. So let's take a look at the code, right? So all these are just configurations, and then we have the DDP. I think DDP is for the distributed something. Yeah, distributed data parallel. We don't need to worry about this. This is basically if you want to run the training on multiple GPUs, but it doesn't affect how we implement the model. So it's just for running on multiple GPUs to do the synchronization and all that. And then we get a batch. So this batch will be similar to a normal machine learning task where you have X and Y, and then you try to fit the model to X and Y, right? So this is very similar to your normal machine learning run. I think this is still supervised learning, if I remember correctly. Train and validation set. So you can see here X is just data from I to I plus block size, right? So for example, this will be 0 to 1024, and then 1 to 1025, and then 2 to 1026, and then you're trying to predict the next token, which is I plus 1 plus block size, right? So basically this is your supervised learning X and Y. And then we have the vocabulary size. So for our Shakespeare character, it will be 65 vocabulary size, but for open web text, which is the larger size, I think the vocabulary size is much larger. Yeah, I think the vocabulary size is somewhere wait, the default vocabulary size is here, right? 50304. And we can ignore this, and then here's the optimizer. So if you're familiar with machine learning, then this is also the same. So basically it looks like it's Adam optimizer. Yeah, using the Adam optimizer, very normal machine learning stuff, nothing too different. And this is the loss function. So loss is just to compute how different is the output compared to the real ground truth, right? So if you're training on Shakespeare, that means even like something like first city Z, how likely are you able to produce N instead of, for example, a Z or something? So that's the loss. So the training's purpose is to actually minimize the loss. That's why the loss should go down, right? So if we took a look at our training code now, so if you try to run this training code again, you can see the loss value is actually going down, right? So these are computing the loss for each iteration and then trying to minimize the loss so that it goes from 2 point something to 1 point something eventually. And then this is just the, I think, root square mean loss, I guess. It's just the mean loss. Oh, sorry, it's not the mean loss. I don't think I made a mistake here. I don't think it's the mean loss. It's just the mean of the loss. Let's see what's the actual loss function here. We should be able to find it here. Oh, it's just inside the forward pass. So if we look at here, it's the cross entropy loss, right? So this is a very standard cross entropy loss that is returned in the forward, and then we get back here as logits and loss. Learning rate, this is very standard stuff for machine learning. Is it actually standard though? It looks very little bit complicated. I guess it's just a bunch of functions to help it learn better. And then this is the actual training loop. For those of you who don't know, this 1 dB thing it's actually weight and bias. So W is weight and B is bias. So it basically refers to this platform where you can track your training progress, like the loss value, learning rate, and all that, and then get a bunch of logs. So this is basically like tracking how your training is going, right? And then, so this is, I guess, the most important part is the forward backward update. We ignore the DDP part, and then this is the actual logic that does the training. Believe it or not, it's just 1, 2, 3, 4 lines of code, right, to do a training. So the important part is just 4 lines. Actually, it's just 3 lines, right? This line is to prepare for the next step. So you basically do a forward pass model on your training data and your expected output ground truths. You get the logics and the loss, and then you use your optimizer to do a backward pass. So what does backward pass mean is, again, if you are familiar with machine learning, you understand this, but if you don't, backward is basically updating the weight so that your model is closer to what you want it to be. Like kind of, you know what the difference is, and then you're trying to make the model behave closer to the actual behavior you want it to be. Right? So a very trivial and probably wrong example to illustrate the idea. So for example here, we have first city, and then you want it to output N, right? But maybe output S, and then the loss will be like, we'll say, hey, this is not supposed to be an S, it's supposed to be an N, right? Then you update the model so that it outputs N, more likely to output N. So that's the backward pass. So basically updating the model so that the weights of the model are more likely to output the correct output, right? So the weights are just a bunch of numbers, a bunch of numbers. Let me see if I can actually print the weights. So to show how it actually works. So let's see here, inside this loading thing, can I actually print the weights here? I think there's some Pico Reader app, right? Pico Reader. I don't know if this thing works, but let's try. So we have a Pico. This is the model file. Oh, it doesn't work. Okay. Let's see. Try another one. Oh, this looks like it can work. So let's try to see what the model is actually all about, right? So this is the model we have trained. Let's see if we can understand what's inside the model. Not preview. Okay, that's weird. Wait, this is not a Pico. Maybe it's not a Pico file. Double check. Maybe I made a mistake here. Where does it save the model? Torch.save. You know what? I'm just gonna ask the cursor to write me a script to read the file. I think it should be able to read the raw content of this file, right? So write a Python script to show the raw content of the Pico file, model weights, etc. Right? So I just gonna ask it to write me a script to open this file so that I can see what's inside. Because I think it's important to understand what's actually being saved in the model, right? So it's trying to locate the file, and then okay, checkpoint file pt, then the KL. Okay, cool. Let's see. I remember there are some tools to do it, but I can't find it anymore. So just like cursor code it out, I guess. Should be straightforward. Okay, I think you can stop here. Okay, so let's keep this and let's try to run this. Okay, so you can see we actually managed to read the content. So you can see it's basically a dictionary of the optimizer, the model, the layer and stuff, and then the configuration, right? And then if we have the show weights here, and then I think it was gonna output the weights. Yeah. So these are the model weights. It doesn't print the raw weights, but this is like basically you can see here we have the linear weight, we have the embedding weights, MLP weights, attention weights, all these weights, right? Maybe I'll ask it to print out the raw weights. That print the raw weights. Add option to print raw weights. Okay. Let's print the raw weight and see what's actually the raw weight. Right? Okay, oh, I think the format tensor, okay. Yeah, looks like it's doing its thing. Use with show weights, okay. Nice. I need to fix the remaining function call. Huh. I think this is the correct command to run. I think you can stop there. Keep. And let's try to run this. You can see it print out the raw weights, right? So let's see. So this is the WTE weight. I think WTE is the, let's see. WTE is the vocabulary size, vocabulary embedding. So you can see here it's just a bunch of decimal, I mean, what do you call this? Numbers? Decimal numbers. And then these are the WPE weights, which is the block for the block. Yeah, again, these shapes will correspond correct to these embedding shapes. And then perhaps more importantly is the attention weights, the linear. Okay, so the linear weights are not very interesting. The MLP weights more varied, so you can actually see this is all there is for the model. Basically a bunch of values to kind of demystify what's actually inside the model. So if we look at let me see what's a good example. I think DeepSeek just released v3.1, right? So if you actually look at what's inside a model like DeepSeek v3.1, it's basically, you know, the same thing. You have the weights, the layer norm weights, the projection, self-attention. So you can see here it's not that different from what we have in terms of the architecture, because they're all just transformer architecture, right, with some new innovations on different things. So you can see here this very simple transformer that we train have all these weights, linear weight, attention weight, MLP weights. This is the actual weight for DeepSeek v3.1. They also have the MLP weights, the attention weights. Yeah, so basically it's the same architecture that you can train yourself. It's not that, if you understand how to train it, it's not conceptually very hard to understand what it's trying to do. So that's the Pico and models side of things. Yeah, so we were on this model, and then we have the backward to kind of make it closer to the actual outcome. So let's try to understand what the backward is, because I think backward is a very machine learning. It's a very important concept in machine learning. So imagine our model weights currently look like this, right? So it's just a bunch of numbers, and then we have the loss value, which is measuring how close our model is to the ground truth, right? So the model output is X, the ground truth is Y, and the loss measures the difference between them. And then with the backwards function, it basically updates these weights so that the output can be closer to the actual value that we expect. So for example, maybe this negative 0.0219 is too small, right? We need to make it larger. So basically update it to instead of 0.0219, we update it to 0.0221, something like this, right? Oh, sorry, make it larger. It means actually like this, right? So make it slightly larger. So that's what this backward is doing, right? And then we're doing it in a lot of times, right? So basically we're doing it like while true, right? So while true, and then we have the break, which is the iteration number. I think iteration number is set to 2000. Yeah, the maximum iteration number is 2000. I think. Yeah, sorry, it's here, right? This is not 2000, but for our Shakespeare one is actually 2000. Oh yeah, sorry, I think it's inside the script, right? So here we set it at 2000. So after 2000 step, it will stop. So I guess that's basically how it works. So yeah, it's not that complicated. It's not that different from training a normal machine learning model. I guess if you have already done some like machine learning training or some classifier or regression kind of thing, you can try to run this yourself. I think it's pretty easy to understand, apart from the attention part, which is, I guess, the novel factor here. So basically this part is the what makes the transformer very interesting. Self-attention and all that. Obviously this is GPT-2. After GPT-2 there's a lot more interesting stuff happening, but this was the main contribution. And if we get rid of the self-attention, it's actually just a normal machine learning model that you can train for normal tasks. Yeah, I guess that's what I want to do. Attention is all you need. Yes. yeah, this is very interesting. So I guess if you are more technical, you can try to read this. I think I found a good lecture on this. This one looks pretty good. It's like for computer science students to understand how it works. I guess it's reading this slides is better than reading the paper. I still couldn't understand fully how it works, but at least it makes it easier to understand compared to reading the actual paper. And obviously this repo you can also download it and try to run it yourself. So you can try to reproduce GPT-2 if you have a GPU. So what I did was I rented a Azure T4 GPU and I ran it for 8 hours. So you can actually train your own GPT-2 model. I'm not becoming a uni lecturer. I'm very bad at math. I can't do a uni lecture. Yeah, so I recommend if you want to try, you can try it to understand how it works. I think apart from the attention mechanism and the matrix multiplication, the rest is quite easy to understand. Maybe I'll do a separate one just on the attention mechanism, because I think that's the novel part that is a big conceptual jump for people who are from traditional machine learning. In this part, maybe you need to read a bunch of papers to understand how this works. But apart from this, everything else is just a normal neural network. Yeah, so if you have been doing Kaggle competitions, you can actually try to run this. Yes, okay. Let's see, that's, oh yeah, I think I planned for this to be 2 hours, but I guess it's actually not that complicated. I'll probably do another one because to be honest, myself, I don't really understand exactly how this attention mechanism works. What are KV and Q and query and key and value. So this is the hardest part to understand. So I'll probably do a separate one that just touch on exactly how this self-attention mechanism works. But apart from this part, everything else is just should be quite straightforward if you understand basic machine learning and Python. So I hope I have done a good job in explaining the rest. Yeah, so that's all for today's live stream. I do other streams, so this is the new How AI Works series. I have some AI coding series, and I do some model testing series, so you can subscribe to my channel for new content. That's Or does anyone have any questions? Please drop in the comment section. Or if you want to, you think this stream is too difficult to understand or too easy for you to understand, please also let me know. I'll try to adjust it. I guess it really depends on whether you have done some machine learning training before with PyTorch or TensorFlow. If I have done it before, it's quite easy to understand. But if you haven't, I hope I've explained this conceptually how it works. Yeah, let's see if we have any comments. Also, another thing I think I want to point out is you can see there's, even though the concept is very simple, there's a lot of lines of code. I think mostly to do with bugs or edge cases from the various libraries, because it's quite finicky, right? A lot of things don't really work sometimes, and you have to kind of work around it. So, you know, for example, this kind of problems, you need to work around this memory leak or something, which is what makes this hard, right? So even though conceptually it's easy, if you actually want to write a code that actually works, it's a lot harder to get it correct. Yeah, I guess that's the thing I want to say. So this is a very good project for people to understand. I think very, very good work here. Does nobody have any questions or comments? Maybe let's take a look at some Devin code. So this is interesting. So people are submitting pull requests made by Devin to improve nanoGPT. So this commit is made by Devin. Okay, so if the warm-up is 0, it will not work. Okay, interesting. Yeah, so it looks like people are trying to add all sorts of weird things to this repo. I guess KV cache must refer to this KV, right? That's my guess. The KV inside this attention mechanism, this KV. Yeah, I'll definitely do a separate video on this. Maybe like as someone who doesn't understand attention, we can actually all try to understand it together. Yeah, that can be something fun to live stream. Yeah, because I think there's a lot of background work, math concepts you need to understand for this. I understand the batch size, understand the sequence size, I understand this, but I don't really understand what is Q, K, and V. Okay, yeah, if there's no more questions, I think that's the end of this stream. Look forward to seeing you for my AI coding stream on Saturday, and maybe next week or Wednesday I'll do another live stream just on the attention mechanism. Okay, see you all. Thank you for watching. Bye.